Hello learners, in this class we'll discuss the codal provisions or design of footings. So as you know, the load is transferred in a building from slab to beam, from beam to column, from column to footing, and then footing to soil. So finally the load is transferred to soil, and soil shall have the sufficient bearing capacity. The SBC, safe bearing capacity of soil, would be such that they can take the loads. Or if you know this SBC of soil, then accordingly you can provide the cross sectional area of the footing to transfer the load. Now again, this SBC is the net SBC. It is not the ultimate load. So that is why we'll take the service. We'll take the service load. Will not take ultimate load, because you are taking this net bearing capacity. You are not taking ultimate bearing capacity. As you know, safe bearing capacity is calculated in soil mechanics by dividing some factor safety with the ultimate bearing capacity. So we take this load as the service load, not the limit state load for the design of foundations. Now you open your IS 456 page number 64, clause number 34.1.2. So first, what is the thickness at the edge of the footing? The thickness at the edge of footing is given is to be not less than 150 millimeter. The thickness at edge shall not be less than 150 millimeter on footings on the soils, and not less than 300 millimeters on piles. So we are not going for pile foundation design. We'll discuss only these footings on soils. So it is minimum. So if you see the how this footing is goes, you find sometimes the trapezoidal like this. The footing is go like this. Okay. So this value should be minimum 150. Can take more. There is no issue, but it should minimum 150 millimeter. Now again, in case of plain concrete pedestal, we have the RCC, so we don't take the plain concrete pedestals. So in case of RCC, but again this load is dispersed from this column to this footing at an angle alpha. Generally this angle is taken as 45 degree. So at angle 45 degree load is transferred. So we can find the area of the footing where the load is dispersed. That we'll see in the later. Next comes these moments and forces. How to calculate the moments and forces, and what are the critical cross sections for moments and forces. Now, in case of footings on piles, so we are not using piles, so it is not required for us. But you should know the computation moments and shear may be based on the assumption that reaction from any pile is concentrated at center of pile. So the reaction that will come, pile is just like column. So in case of pile foundation, whatever this reaction of pile, that will be taken as the center pile and as a concentrated load. So let us see the critical cross sections of the bending moments. Go to page number 65, clause number 34.2.3.2. So this is gives this greatest bending moment to be used in the design of an isolated concrete footing which supports a column, pedestal, or wall shall be the moment computed in the manner prescribed 34.2.3.1 as section indicated follows. So what is said in 34.2.3.1? So prior to this, you can see what is 34.2.3.1, that is regarding the cross sections. The bending moments at any section shall be determined by passing to the section a vertical plane which extends completely across the footings and computing the moments of forces acting over the entire area of the footing on one side of the set plane. I can explain here. You see there is a footing. If you take the section, this plan of this footing, let the same things be given here. We take a plan like this. Okay, it is the plan of this footing. Now, if you take a cross section at here, so while extending it will so there will be a column here. So for this there will be a column here. Okay. Now, if you will take this section will entirely cross from one side to the other side. So one side of the plane will be considered for calculation of bending moment and shear force of that said plane. That is the meaning of this clause. So accordingly, you can find the cross sections greatest cross sections for bending moment. So what it says, at the face of the column, pedestal or wall for putting support and concrete column pedestal. So at the face of the column we have to take this critical section. Halfway between the center line and edge of the wall for footings under masonry wall. So we are not going for any designing masonry walls. Then halfway between the face of the column and pedestal in the edge of the gusseted base or footing under gusseted base. So only the requirement for us is only this, because we are going design isolated footing, single foundation for a single column. Neither we are going for pile foundation, nor for mat foundation, or not for the continuous or combined footing. So at the face of the column, that means in the previous diagram, if you go to this again that diagram where it will be easy to understood. Now here you see at the face of the column means that if I will draw here this plan. So this is my plan. Okay, this is the column. This is the footing cross elevation. Now you take a plan. So at the face of the column means, so this is the face of the column. You draw a line here. So this is the face of the column. So your column is here. Okay, your column is here. So this is the face of the column. So one side of the plane will be taken either this side. You can also this is one direction, X direction. You can also take Y direction. You can also take also on this line. So but the maximum value you have to take. One is this direction. You can take this is equal to B, the width of the footing, and this is equal to L, that is the length of the footing. Okay, so length and breadth is given. So either you take a cross section like this extending along the face of the column or along the face of the column. Calculate bending moment along this direction, bending moment the other direction. So the maximum bending moment is to consider for design. So generally we found this area of this footing by dividing the load divided by the SBC. If you divide load by SBC, you can find out the area. So then you provide some area or give a size of this footing. Once you know the size of footing, then load by area will give the stress. The stress that will be applied to this footing from the soil. So that value you will get from dividing load by the area. So this intensity of load multiply by this intensity of load multiply this area will give the force. Where the force will be applied at the center. Then this will act as a concentrated force multiply by this distance will give the moment. That means if you want in this direction, these loads in this direction, find out W is suppose W or P is the intensity of load multiply by B. Okay, so this is equal to B, and then what is this value? This area. So what is this length? This length will be, if this is equal to A of the area of the column, it is a rectangular section. So L minus A by 2. So this will be L minus A by 2. Okay. So L minus A by 2 into B is the area multiplied by P is the intensity of the loading. So P into L minus A by 2, and it will act at half of this. So L minus A by 2 by 2. So L minus A by 4. So multiply this will be equal to P into L minus A whole square by 8. L minus A whole square by 8 into B. B is the multiply this area. So B into L minus A by 2 into L minus A by 4. So that is the moment in this direction. In the other direction, P into L, and this will be B minus small b, B minus B by 2. Okay. B minus B by 2, then CG will be B minus B by 4. So we'll find P into L into B minus B whole square by 8. In the other direction, find the moment is coming P into L into B minus B whole square by 8. Okay. If it is a rectangular footing, if it is square footing, moment on both directions will be same, because if it is a square column and square footing, the dimensions will be similar in the both directions. So it will be one value will be sufficient. So this is how we calculate this moment. We will see details while discussing a example problem in the next lecture. So this is regarding your calculation of the maximum bending moment. Then how to calculate shear? There are two kind of shear again here. So you see one-way shear and two-way shear. You see shear and bond. The shear strength of footing is governed by the more severe of the following two conditions. The footing acting essentially a wide beam with a potential diagonal crack extending in a plane across the entire width, as we have discussed. The critical section for this condition shall be assumed as a vertical section located from the face of the column, pedestal or wall at a distance equal to effective depth of footing or footings on piles. Okay. So the vertical section will be taken like this way. The critical section shall be vertical located from the face of the column, pedestal or wall at a distance equal to effective depth of footings or footings on piles. So you can take this again, you can go to that drawing, you can find out where it is taken. So if you draw this cross section again, the plan. So where is the critical section for this one-way shear? It is taken. If this is your column, then you can take at a distance D, effective from this face of the column. So that is the critical. So you can take a load on this side. This is your shear force. The intensity of loading multiply this area. This area is B, and this will be L minus A by 2 minus B. So this will be, this distance will come as L minus A by 2, okay, minus B. If A and B, A is the this, L is equal to this, and B is equal to this. So similarly, you can also find in the other direction here. Here you can also find this critical section for shear, the other direction, and that will be B minus B by 2, B minus B by 2 into minus D into L, okay, into P. So this is the shear force on this side. So critical section is taken at a distance D from the face of the column on either side, or the rectangular sections. So next there will be a two-way shear. This is one-way shear. We are taking either this side or that side. Then you go for the two-way shear. What is the next clause says? Two-way action of the footing with potential diagonal cracking along the surface of truncated cone or pyramid around the concentrated load. In this case, the footing shall be designed for the shear in accordance with the appropriate provision given 31.6. So now go to the page 31.6 of this 31.6 of your page number is page number is 57. Go to page number 57. So now in page 57, you can say at this now page 57. Okay. So what is written here? Shear in flat slab. So the behavior will look like a flat slab on there. So you can see the critical section for shear. Where the critical section? The critical section here shall be at a distance D by 2 from the periphery of the column, perpendicular to the plane of the slab, where D is the effective depth. See the figure 12. So see the figure 12. The figure 12, the critical section for shear is given. Now you go to this figures given. If it is a rectangular, D by 2 from all the sides. So this is the critical section for shear. So if your plan is like this, okay, suppose this is your plan of your footing, and you have taken critical, this is the critical, so load will come from this side. So what is the load? So this portion of area will give the load. Now the total is L into B, okay, and this is D by 2, this side D by 2, this side. So this distance will be A plus D, okay, from here to here it will be A plus D, and from here to here it will be B plus D, okay. So what is the area that will contribute the shear force? L into B minus A plus D into B plus D, okay, A plus D into B plus D. So this much of area multiply by your intensity of load will give the shear force for two-way shear calculation. So two-way shear will come like this. For any circular or for any other kind of sections, you would find your critical section for shear. You can see there are many sections given, the different type of section for which the critical section are d by 2 from the periphery. So this is how you calculate the shear force. Once you find the shear force, then how to calculate shear stress. Calculation of shear stress is the shear stress tau b shall be sum of the values of calculated according to 31.6.2.1. How to 30.6.2.1? This is V by B0D. You see what is written here? What the tau v? Tau v is equal to V by B0 into D. What is B0? B0 is the periphery of the critical section and D is the effective depth. So you take the periphery of the critical section. Wherever you take the critical section, take periphery. So critical section is A plus D. We have seen the critical section was A plus D into B plus D. Okay. A plus D plus B plus. So what is the periphery? Periphery will be A plus D plus B plus D into 2. So the B0 value will come out 2 times A plus D plus B plus D. Okay, the distance along the periphery. So take this value as your B0 value and calculate the tau v value. This is how to calculate tau v value. Once you calculate tau v value, then you check that what the permissible shear stress. Now, when the shear reinforcement is not provided, because again it is a slab, footing will behave as a slab, and the shear reinforcement is not provided, the calculate tau v shall be less than Ks tau c. So your tau v shall be less than Ks tau c. But the Ks and what is tau c? You have to see here. Now see the next page. So what is your equation? That tau v we have calculated shall be less than equal to Ks tau c. What is Ks? Ks is equal to 0.5 plus beta c, but not greater than 1. So maximum value of Ks is equal to 1 or 0.5 plus beta c, whichever is less. It cannot be more than 1. So beta c means short side to long side of the column. Column has a size, it is a rectangular size or square size. If it is square, it is 1. If it is a rectangular, then short side to long side. Short side to long side means it will be less than 1. So 0.5 plus beta c, calculate. If the value is less than 1, take that value. If it is greater than 1, take value is equal to 1. Tau c is equal to 0.5 root over FCK in limit state method, because we are designing for limit state method. So the tau c will be 0.25 root over FCK. So calculate tau c and tau b Ks, then Ks shall be less than tau c. When the shear stress at the critical section exceeds the value given above, if tau b exceeds this, tau b shall be less than for no shear. If it exceeds that, but less than 1.5 tau c, shear reinforcement shall be provided. And if the shear, if this if the flat slab shall be redesigned. Okay, if it is less than tau, what it say, if tau b less than Ks tau c, no shear design. If it exceeds tau b exceeds Ks tau c, but less than 1.5 c, then it will be shear design will be done. If it is more than 1.5, it is 1.5 tau c, there will be no shear design. So these things you should see there, check for the shear design. Now let us go to our main page. We have checked initially page 54 to 64 to 66. Okay. Now we get this two-way action of footing and one-way shear, two-way shear. So what we will do basically, you have to find the depth from this bending criteria, then check for one-way shear and check for two-way shear. If the depth requirement is more, then you take more depth, and that is the final value of D. So effectively calculate from one-way shear, then from two-way shear and bending. These three criteria. First is flexure, then one-way shear, then two-way shear. Out of these, the maximum value of D required for any case will be taken as the final effective depth. Then add the cover. But the cover is generally we have seen 50 millimeter for these footings. Then diameter, half of the diameter rod. So accordingly you have to find the overall depth of this slab. That we'll discuss while solving a problem. So next we will go for this development length check. Now this section is for pile, we don't record pile. The critical section for checking development length and footing. So what is the critical section for development length and footing? So you have a footing like this, okay, and you have this section like this. Now what it says, you have the critical section is same as the described for bending. For bending we have taken the face of the column as the critical section. So you calculate the length of available from here to here, and this length shall be more than LD. What is this length? You have the along the length and breadth. Because the breadth is less, you take the B value. So this distance will be B by 2, okay, E by 2 minus B minus B, B minus B by 2, B, this is the B minus B by 2 minus cover, because you have to provide cover here also. If the rod will come like this, it will stop here, you have a cover here. So this value shall be greater than equal to LD. So you have a sufficient length for development. So check this. So this is the check for development length. Simple check you want to do. So the critical section for development length is same as the critical section for bending moment. Remember this. So now once you check, this is for bending check, then you have to see for this reinforcement, how to provide tensile reinforcement. We calculate the depth, we have calculated the bending moments. Now how to provide the reinforcement, because this is a two-way slab, reinforcement will also provide in the both direction, x direction and y direction. So let's check. The total resistance reinforcement at any sections are provided a moment resistance at least equal to the bending moment on the section calculated according to 34.2.3. So here we have calculated the bending moment. The same bending moment we have used here, mx and my for both directions. And total tensile reinforcement shall be distributed across the corresponding resisting section as given below. In one-way reinforced footing, the reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. So if it is a one-way footing, then we have to provide like this. But we have the two reinforced sections. We have not one-way reinforced, two-way reinforced. In two-way reinforced square footing. Now footing is again either maybe rectangular or square. In square footing, the reinforcement in each direction shall be uniformly distributed across the full width of the footing. Because in square footing, both moments will be same in the both direction. Steel will be same. So you find a number of bars. The number of bars shall be provided along the entire width. Either you provide in this side entire width, or you can provide entire width. So you find the AST and then provide along the entire width. But in case of rectangular footing, if you have a rectangular footing, how to provide this? Because the reinforcement will be different in both different directions. So this clause says in two-way reinforced rectangular footing, the reinforcement in the long direction shall be distributed uniformly across the full width of footing. So the long direction steels, let me draw here a footing section. So one is the long direction, one is the short direction. What it says, the long direction steels shall be provided uniformly across this width. So you know the B value, so you provide accordingly here. This is the B value, leave the cover on both sides and provide. Now this is your L value along the length. So the short direction steels out to provide maximum will come along short direction. In the long direction shall be distributed uniformly across the full width. For reinforcement in the short direction, a central band equal to width of the footing shall be marked. So this is L, B is less than L, so mark here B. You mark here to here is your B value. Okay, this is your width value. You mark along the length centrally, same on both sides. So marked along the length of the footing and portion of the reinforcement determined in accordance with the equation given below shall be distributed on the central band. So what is the steel provided on central band? What is the steel provided on the edges? So the central band will provide reinforcement in central band is equal to by total reinforcement is equal to 2 by beta plus 1. So you have calculated the total steel. Out of total steel, a part will provide in the central band. So 2 by beta plus 1 into total reinforcement. What is beta? Beta is the ratio of long side to short side of footing. L by B ratio. Sorry, long side to short side. L by B ratio. L by B ratio means this will be more than 1. So this will be more than 2. So a portion of the steel provide the central band. So whatever steel find the number of bars, provide uniformly across this width. Then the remainder. So once you find this central band, the remainder of the steel will be uniformly distributed on the outer portion of the footing. So you have the footing on the edges. So accordingly, you provide the rest of steel. So finally, how to transfer the loads? The load transfer mechanism. Load at the base of the column. So load will be transformed from base of the column to the footing as initially I have discussed, and they will be provided at an angle 45 degrees. So how to check that the bearing stress is within the permissible limit? Load will transfer like this. So you have to find the things. So this is just like a frustum of a cone pyramid. The compressive stress in concrete at the base of a column or pedestal shall be considered as being transferred by bearing to the top of the supporting pedestal or footing. The bearing pressure on the loaded area shall not exceed. So this load will transfer through bearing at here. So that means the load divided by A into B. That is the area of the column. That is the bearing stress. The bearing pressure on the loaded area shall not exceed the permissible bearing stress. So that is permissible bearing stress that we will see in the next page. Shall be direct compression multiplied by value equal to this but not greater than √2. So what does it mean? I will see what the permissible value for working stress method of design. Permissible bearing stress concrete is 0.25 and for limit state it is 0.545. So we will take the 0.45 FCK because we have the limit state method. So the bearing stress will be equal to 0.45 FCK. Now 0.45 FCK means, so what will the value now? So let's check the bearing stress, that is W by A into B. This is the bearing stress. But it says the bearing pressure on the loaded area shall not exceed. That means that shall be less than the permissible bearing stress, that is 0.45 FCK. We have find for limit state it is 0.45 FCK. Then multiply a factor. What is that factor? The factor is equal to root over A1 A2 but not greater than 2. So if root over A1 by 2 is greater than 2, you have to take in 2. If the value is less than 2, you have to take the value less than 2. So please calculate A1 A2, take square root. Okay. What is A1 A2? A1 A2 is, what is A1? Now A1 is equal to the supporting area for bearing of footings which in sloped or stepped footing may be taken as the area of the lower base of the largest frustum of a pyramid or cone contained wholly with the footing and having for its upper base the area actually loaded and having side slope of 1 vertical to 2 horizontal. That means this spread will be equal to 1 vertical 2 horizontal. So if it is your value is A, larger value A, so this will be 2A and this side also will be 2A. Okay, so 2A, this is D. This will be equal to D, means this is 2D. This will 2D, this will be 2D and this is equal to A. Okay, so it will be A plus 4D. So A plus 4D will be the base, that the base of the frustum of a pyramid or cone. So the area will be A plus 4D whole square. So this area will be A plus B 4D whole square. So A1 is nothing, A plus 4D whole square, and A2 is equal to loaded area of the column base. So find the area of the column base and then divide these two, that will be the value and shall not be greater than 2. So this is, and so this is the check for the load transfer at the base. So these are the steps for the design of, once you have check all these things, then you have the detailing of reinforcement. So all the details we will discuss in a example problem, and this concludes these guidelines for this design of isolated footings. Have a nice